Hey folks, welcome to this episode on uncertainty, significant figures, and rounding in measurement. So let's say, for example, you needed sugar for a lab. You're told to bring it from home. Using a kitchen scale, you weighed it out in grams, and you got 200.2 grams. However, when you're walking to school, you lost exactly a quarter of a cup, so you need to replenish it in the lab. The scale in the lab was a little bit more accurate, or a little bit more precise, and you measured out 50.236 grams. So when you put the 50.236 grams into the 150.2 grams that you had left over, how much can you honestly say that you had? Did you have 50.436 grams, or what do you know? Okay, so this is what we're going to be talking about in this next episode and two. So when we measure things, we have a certain amount of uncertainty. If we were looking at this graduated cylinder, we can for sure say that we have at least, well, here's 15, 16, 17. We have at least 17 grams, but we know that we also have less than 18. That we can say for certainty. But 17 in what? Well, it all depends on how you're reading it. If you read from here, it's going to be different from if you read from here and you read from here. It also depends on if you're going to read this side or the bottom of the meniscus. So there is a certain amount of uncertainty when we measure things. Now, we may not agree on the actual volume, but we can agree on two ideas. One, that every measurement has units. For example, in the previous graduate cylinder, the units would be millimeters. And that every measurement has uncertainty. Okay, we can't be exact with our measurement because there's always going to be some room for error. And we use two terms to kind of explain this: precision and accuracy. Accuracy is how close you get to the known or target value. So in the case of here with the little cat, the target is the hand. And we want to put the mittens on, the kitten. So we need to get on the hand. So there's a certain good accuracy because it's all around this area. Versus here, the idea of precision is the reproducibility, or the ability to repeat these measurements, or in this case, putting the glove on. So even though it's not accurate, it's not on the target, the trials, or the different trials of putting the glove on, are very consistent. They're all in that 1 space. Here we have good accuracy, bad precision. It's all over the place. Here we have good precision and bad accuracy. This is where we meet in the middle. So once again, accuracy refers to how closely a measurement matches the true value or the known value. And precision refers to the reproducibility of that measurement. So if we're talking about this little arrow shooting bullseye, the accuracy would refer to whether or not you get it onto the bullseye. If you had it over here on the black or here on the blue, that wouldn't be good accuracy because your target is the center here. So in this case, this individual shot 3 arrows. They were all in the bullseye, very good accuracy. Precision refers to the reproducibility. So let's say, for example, you were in fact aiming for this middle, but you kept getting all 3 shots in the blue, right in this little area. Well, that would be good precision, but poor accuracy because you're reproducing it all in this area, but you're not close to your target value. We can also talk about precision in terms of exactness, in terms of a number description. So this allows you to say, for example, when you're talking about a decimal, if you have 2.132, that's a certain level of precision because you have significant figures over here. Now, if you're not familiar with significant figures, stay tuned. We'll be talking about it in a second. So accuracy and precision, again, good accuracy and good precision means that it's reproducible, that it has been reproduced, and that it's on target. So here it's reproduced and on target. Here, it's kind of on target, but it's not reproduced very well. So accuracy is good, precision is bad. Here, it's been reproduced very well, but it's not on target. So good precision and good precision and poor accuracy. And here, it's just bad accuracy and bad precision. Hasn't been reproduced, not on target. It's all the way bad. So again, when we have this little photo here, we're trying to measure a nail, and when it comes here, we have this little ruler over here, and I'm trying to measure this nail, and we can see that, well, it's more than 2.5 centimeters, less than 3. We can get a little bit more precise with that. It's 2.6, 2.7, 2.8, 2.9. Okay, so it's somewhere. We know that it's between 2.8 and 2.9. So if we expanded that over here, we can see our 2.8 and we have 2.9. But what we don't see on the ruler are these little graduations. Okay? So when we estimate that kind of looks on a regular size ruler We would say that's about, I don't know, 2.4, 2.84 or 2.85, 2.86. It's hard to tell. If we had these little subgraduations, well, again, we can be a little bit more precise. If we blew it up even further, we could actually have subgraduations on that. So when we're talking about a measurement, it's never exactly precise, but we try to estimate its precision using some certain rules. So again, different people might see this a little bit differently. These are for sure. We know that it's 2 centimeters, we know that it's 0.8 centimeters, but this last digit is an estimated number. So when we try to make some meaningful conclusions from these measurements, we use these idea of significant figures to generate some meaningful conclusions. Okay? And we need to be able to have some rules to be able to combine data into some kind of meaningful information. So when we have a couple of measurements and we're adding some different numbers, we need to be able to use that in a way that will give us the lowest amount of kind of made up data, if you will. So some of the rules here, and we'll talk about non-zero integers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Non-zero integers are always significant. So whenever we have here, in the first case we have 1457, we have 4 significant figures or significant digits. In this one over here, we have 3 non-zero integers. So that means we have 3 significant figures. That's very simple. When we talk about zeros, there's a few different rules, and it all depends on where they are. In the first case scenario, we have leading zeros, which are leading the non-zero digits. So in this case, what they're actually counting as they're just placeholders. We could actually change this into 8.6 times 10 to the negative 3 of whatever unit that is, and see that there's only truly 2 significant figures. So the leading zeros are just placeholders, and they never really count. So in this case, we have 2 significant figures. Zeros that are in between 2 non-zero integers are always significant. So as we can see here, we have 2 zeros that are trapped between a 3 and a 5. Those count. So altogether, we have 4 significant figures. Now, trailing zeros are a little bit different. If it's written with a decimal point, we actually do count them. They do show a certain amount of precision. So in this case here, 100, we only have 1 significant figure. These ones, we're not sure if it's exactly 100 or if it's a measured 100. Measured numbers, for example, if I measured and I counted the number of apples and I said I had 100 apples, well, there we had 3 significant figures. But if it's a measured value, for example, I had a nail and it kind of measured to about 100, well, I'm not too sure about these. So these zeros are not going to count. It's only going to be 1 significant figure. If we had a decimal, and this is a very weird way of putting it, but you might see it sometimes. If we had a decimal in the back here, that means we had exactly 100. So that would mean 3 significant figures. And finally, we have 120.0. This is 4 significant figures because let's say, for example, we were weighing something. We were weighing a watch and it weighed 120.0 grams. That means on the scale it has registered as 120.0. This 0 could have been a 1, it could have been a 2, it could have been a 3, but no, it was a 0, which means that it's precisely 0. When we're talking about exact numbers, this means that either we were counting them or we were determined by a definition. So once again, if I was counting apples or oranges and I had 5 in front of me, that would be significant. If I had 50 apples, then I know that those are all both going to be significant because there are indeed 50 whole apples. The other way that when we're talking about counting is the definition. So in this case, 1 inch is equal to 2.54 centimeters. These are all going to be significant. So take a moment and try to practice here, see if you can apply these rules, and we'll come back with the answers. So go ahead and pause the video now. So welcome back. Here are our answers. There shouldn't be any surprises. For example, we can talk about this 200. Again, there's no decimal here, so these zeros are not significant. Here, this 0 is captive, which means it is significant, but the leading zeros are not, so there's 3 over there. The 0 over here is after a decimal, so that will be significant. Captive 0, significant. And here, when we look at this, we should actually have this value should be 5 because the following zeros are after a decimal place, which means that they show significance there. So this should be 5 over here. And here again, after decimals, we have 4. And here's a counted value. So there's 60 minutes in an hour. That's actually a definition. So we precisely have 60 minutes in 1 hour, so that is significant. Same thing here. Some person ran 500 laps in the race. They ran 500. They didn't run 499 and it was rounded. It was exactly 500. So rules for rounding are pretty simple. When we talk about rules, these are the two basic rules that are given. If it's less than 5, then it rounds down. So in this case, 1.33 would just be 1.3, assuming we're just rounding to two significant figures. And if it's greater than 5 or equal to it, we generally round up. However, we're going to change this in for chemistry. When it is equal to 5, we're going to be using an even-odd rule, and we'll talk about in the next round. So our rules were going to be, if it's less than 5, we round down. If it's greater than 5, we round up. If it's equal to 5, well, stay tuned. So let's look at this one over here. Round off the 52.394 to 1, 2, 3, and 4 significant figures. So for the first one, just round to 1. The second one, round to 2, 3, and 4. So pause the video. We'll come back to see how you did. All right, so welcome back. If we round it to 1's figure, that means that we are trying to figure out what this will do. Since that's a 2, we're going to round down, so we would have 5. And over here, we would see, and that would be, this would actually be in terms of, we'd have 5 times 10 to the power of 1. Okay? Because what we only need is one significant figure, but we still need to show that it's 50. So it would be 5 times 10 to the power of 1. If we round it to 2 decimal places, again, we'd look at 3. Is it higher or lower than 5? And it's lower, so we round to 52. For 3 significant figures, we have to look at number 9. So number 9 is greater than 5, so that means we're going to round the previous digit up. So it's going to be 52.4. And finally, for rounding to 4 significant figures, well, that's a 4, so we're going to round down. We're going to keep it as 39. Now, when it comes to rounding 5, what we do is we look at an even and odd. So in this case, we round it up so that it's going to be even. Okay, so it's going to the digit that is being rounded off, so it's going to be even. So in this case, when we look at this and when we're equal to 5, we want to change the digit prior to as even. If it's already even, we leave it as it is. So in this case, the first one says round 726.835 to 5 significant figures. So that would be up to here. So what we need to do is we're trying to decide on what to do with 3. Now, since the following number is 5, what we're going to do is we're going to change it into our even rule. So we're going to turn the odds into even. So that would be 726.84. Now, for the second one, we have 24.8514. We want to round to 3 significant figures. That means here. So we're trying to decide what to do with this 8. And what we see here is that the 8 is already even, so we just keep it as 24.8. So that's it for us for this episode. Thanks very much for watching. See you soon.